ni kita tak buat dia dengan terancang. Oh, ada international student inside the, in our class.
Yes,
Is there any
doctor. Assalamualaikum.
is there any international student?
Yes, doctor. I am Iftikhar Ahmed. I am international student.
Oh, I'm
Assalamualaikum.
sorry, you should remind me earlier. Okay. Uh, so speak in English from now on. Okay. So
Okay, no
basically, the causes of flood are due to natural flood, man-made flood, and also climate change flood. So what we're concerned with in this class is that flood due to man-made lah. Okay. So that's why that's why we need to do some mitigation during our development so that this will not cause aggravate the situation which cause flooding furthermore. Okay, so rapid development is one of the main causes of flooding, where we conduct our development without any without sustainable sustainable measures. Okay, we can not avoid development. Okay, because with increasing population, we need to provide more houses, more buildings, and so on. Therefore, we cannot avoid development. But what is important is that we must provide the developments, the development sustainably. Okay, we try to plan the development in such a way that it will not cause major impact. For example, like when we do our development, we try to control the erosion from the project site, because erosion will cause siltation inside our rivers, and therefore the conveyance capacity of the river will be severely reduced. Okay. Okay, that's why we see that one. The one below, right under the rapid development is drainage problem, such as constriction, insufficient capacity due to siltation. Okay, whenever there is siltation, that will reduce the conveyance capacity of the river, which will cause flooding. Okay, and the other factor is that climate change flood lah. So over the years, we are experiencing this climate change effect, which causes some very intense rainfall which cause rapid will cause flash flood. Okay, next slide. Okay, so introduction to MASMA. This is the manual, or it is in Malay actually. MASMA stands for Manual Saliran Mesra Alam, or it is environmental friendly drainage manual. Okay, so basically this manual provides some guidelines on how to conduct our development so that it can be a sustainable development. Okay, so for this class you need to refer to MASMA for your design. Okay, so you need to design, for example, like temporary earth drain. You're going to design the sediment basin. So all this you need to refer to this manual. You can get this manual from the JPS site or the Department of Irrigation and Drainage. So you can download the manual for free. Okay, so this manual is readily available and you can download it. Okay, so basically what is MASMA? Next slide. Okay, what is MASMA? Overview and this is the new version of the second edition of the manual. So the first manual was published in 2001 and the second edition was published in 2011. After 10 years, 10 years later from the first edition, the Department of Irrigation and Drainage, they upgrade the manual to second edition, whereby they improve some of the topics and they drop some of the topics based on the feedbacks from the users of the manual, the first edition manual. Okay, next slide. Next slide, please. Okay, so basically this new drainage manual is to replace the old manual which has been outdated, because the approach is different. Because the previous manual is the approach is based on rapid disposal and hard engineering, but the new manual is based on control at source. Okay, next slide, please. Okay, so this approach, the new approach, for the first manual, first edition manual, urban stormwater management manual, is the concept is control at source, whereby we will try to control the problem at the site. Okay, not to pass the problem to the downstream area. Okay, next slide. Okay, so this is the cover for the second manual, the second edition manual. Next slide. So the historical fact is that the first manual was endorsed by the minister in 2001. Okay, next. And then, as you can see, the second edition was launched in 2011. Okay, next slide. Okay, so the manual strategy for this the drainage manual strategy is to incorporate surface runoff control, to incorporate surface runoff control, and then management and delayed disposal. Okay, so the strategy is to how we can manage the surface runoff, or how can we control the surface runoff and manage it and delay the disposal. Okay, for example, like when it's heavy storm, we store the water inside a pond, and then later on we release it gradually after the rain. Okay, so basically that is the strategy. Okay, so we don't want to release the water as soon as possible, like in the concept in the earlier manual, the 1975 manual. So that is more on rapid disposal. Okay, this should result in flood flow reduction. So based on this strategy, we can achieve a few objectives, such as flood flow reduction, water quality improvement, so our river water become more cleaner, and ecological enhancements. Okay, so basically we improve the water quality, and therefore the water become clean, and we can attract more fishes to come to our river. Okay, so basically the high quality fishes such as ikan jelawat, ikan patin, ikan kela, um, will be swimming in this river. So therefore, it indicates the river water quality is excellent, is very good. Okay, so that's what we're hoping. But in our urban rivers, normally the fishes are not of that high quality. For example, like we have this mud skipper, and other fishes that is not very expensive actually, because it's not very high quality fishes. But that is the purpose. We try to bring back, eh? we try to bring back this better quality, so that we can bring back the fishes into our streams and rivers. Okay, next slide, please. Okay, there are a few key elements within MASMA, the manual. One is quantity control, the other is quality control, and third one is erosion and sediment control. So basically, the three main components of this MASMA drainage is to control the surface runoff, which is under the quantity control. The quality control is to remove all the pollutants, such as gross pollutants, such as plastic bottles, food waste, and so on, food containers from our rivers, so that our rivers can look very clean. Okay, so if you happen to be in Malacca, you can try the river cruise. You can see the river is coming cleaner over the days, over the years, because it used to be quite dirty, but the effort from the state government to improve the river water quality has bear fruit, when the river is quite clean nowadays, but except that certain stretches you can there's a bad odor. Okay, so that comes from the direct discharge from the household, but that one has been taken care also. Okay, similarly we have similar project in Johor Bahru, which is Sungai Segat. Okay, the government is trying to improve the river water quality, because river Sungai Segat used to be one of the dirtiest river in Malaysia, but now it's getting better to class 2 or class 3. You can see fishes swimming again in the river. Okay, so basically, they have successfully removed some of the rubbish from the river, and also from the organic pollutant from the household and buildings and so on. So now it's getting better. Okay, and the third one is erosion and sediment control. So still Malaysia is still developing country. So there are so many development constructions projects going on. So previously there is no control from this construction site. Therefore, uh, a lot of erosion happening within this project site. And what happened when the after the erosion, the eroded material will be transported by the surface runoff and deposited inside the rivers, streams, channels, water bodies, and so on. So what happened when the rivers is being silted with this sediment? So the conveyance capacity is reduced significantly. So now the river, instead of the capacity, it can carry about 20 meter cube per second of flow. Now when it is reduced by half, so it can only transport about 10 meter cube per second. Okay, okay, so that is why the government feel that it's very important that we control erosion from the construction site, eh? And therefore that will prevent the material from leaving the construction site into the rivers and water bodies. Okay, so basically, Department of Environment, they have the authority to issue stop work order to any construction site which doesn't have this erosion and sediment control BMPs within the site. Okay, why? Because it is very important. Because if not, you'll see that the river turns into yellowish color or teh tarik during or after rainfall. Okay, next slide. So this is the cover of the first edition manual. Okay, so basically the manual, it is for to guide for sustainable stormwater management. So basically this manual provides some some provide some design criteria and so on for sustainable stormwater management. Okay, also provide some guidance for detailed design of stormwater management facilities and design application. Okay, next slide please. Okay, so basically these are the three main components just now that we have shown earlier. So one is erosion and sediment control. Why it is important? Because we don't want the rivers to be silted, or we have mud flood inside the river. You can see that some of the some of the flood that happened previously in some other countries. For example, like in Japan, you see the flood water is very clean. Okay, the water that enters into the building is very clean. You can see it's quite clear. But in Malaysia, the flood water contains a lot of mud. Okay, so especially after flood, so there will be some volunteers going from house to house to clean the house because the house is filled up with mud. Okay, so this is what happened because we didn't control our sediment and also erosion from our construction site. Therefore, that is very important that we provide some of these BMPs or best management facilities to control erosion and to control sediment from leaving our construction site. And then we have also some stormwater quality control to remove this pollutant, gross pollutant from rivers. Okay, but we are not going to cover this in our class IDP1, but this one will be covered in the option class, urban stormwater management, and also stormwater quantity control. Okay, next slide. Okay, that's about it. Okay, next slide. Next slide. Okay, so as you can see, this is kawalan quality or quality control. So during construction, we have to propose some BMP such as silt fence, as you can see in the lower left-hand corner. So that is the picture of a silt fence. We propose this in our construction site to prevent erosion or sediment from leaving our construction site. Okay, and then to filter out the sediment, we introduce check dam. So the middle picture is check dam where we gather rocks and we arrange it in such a way that we can reduce the velocity and filter out the sediment. And finally, on the third one is the picture of sediment basin. The purpose of this sediment basin is to filter out or to allow the eroded material to settle within the sediment basin. Okay, next slide. Next slide, please. Okay, so okay, this is something just additional topics on the difference between new manual and old manual. Okay, the second edition dengan the first edition. Okay, okay, just forget about it. So, okay, we finished topics on the introduction to MASMA. Okay, okay, okay. Okay, never mind. Leave it. We go out and then we open the other slide. The other topic, soil loss slide. Okay. Okay. Soil loss estimation. Okay. So this topic will cover on the estimation of soil loss from a construction site. Okay. Okay. Next slide. So basically, we have to know what is erosion. Okay. And what is sedimentation, because this is the main causes of the problem. So once we identify the causes of erosion and how to prevent it, then only we can prescribe the right solution or the right medicine to our problem. Okay, so basically, what is erosion? Erosion occurs when soil particles are displaced by raindrops, moving water, or wind. Okay, so this is basically what erosion is. Erosion occurs when the soil particles are displaced, okay, by raindrop. What happens is that when the raindrops drops on the surface of the earth, okay, so it breaks the bond between the soil particle. Okay, why it happened? Because there is no cover to protect the soil from erosion. Okay, so whenever we want to do development, so the first thing we will do is that we're going to remove all the trees, the grass, and the shrubs, the bushes, and so on. Okay, once we remove all these, the soil is without protection, because all this while, all the trees and bushes, shrubs, they provide protection for the soil. Okay, but once we remove it, then there is no more protection to the soil. Okay, so what happens is that when it rains, the raindrops energy, okay, will detach or displace the soil particle. It will break the bond between soil particle, and therefore the soil become loose. And then when surface runoff occurs, it will carry the eroded material to the downstream area. Okay, so basically erosion is the process of detachment. It is being broken down. Entrainment is being flooded, and transport and being carried downward to of the soil particles from their place of origin by the agents of erosion. What are the agents of erosion? Uh, Raindrops, moving water, and wind. Okay. So of course, in Malaysia, or in tropical countries, uh, the major factors are raindrops and moving water. Wind is not much of factor, not like in this arid region. Okay. Okay, and Malaysia also is one of the country that is being blessed with abundance of rainfall. Okay, so how much rainfall that we receive in a year is about 2,500 millimeter. Okay, can you imagine how much is it? How whether it's a lot or not, we can just compare to other countries. Okay, for example, like countries in arid region, because last time we have a project in Saudi Arabia, the average rainfall station in Medina at that time is about 60 millimeter a year. And when we compare it to what we got in Malaysia, it's about 2,500 millimeter. So basically, the amount of rainfall in some area is very much less than what we receive in Malaysia. Okay, so that is the average rainfall in Malaysia. Of course, in Malaysia, we have some places we receive a lot more rainfall. For example, like when we did this study in Sarawak, in Bintulu last time, so the average rainfall is about 5,500 millimeter, almost double of the national average. But of course, there are also places in Malaysia that receive very much less rainfall. For example, like some of the city like Raub, they receive less than 2,000 millimeter a year. Okay, but still much more higher than we what they have, what was recorded in city of Madinah in Saudi Arabia last time. Okay, so basically Malaysia is blessed with a lot of rainfall. Okay, therefore, if we don't protect our soil, then a lot of this soil will be eroded and transported to the downstream area. Okay, next slide, please. Okay, what is detachment? Okay, detachment is the removal of soil particle from the soil surface. So the energy from the raindrops, uh, the kinetic energy produced by the raindrop when it hits the soil surface, uh, the energy is quite tremendous that it can break the soil particle bonds. Okay, so as a comparison, when you ride a motorcycle during rainfall, when the first drop of the rainfall hit on your arm or your exposed hand, you can feel uh, the energy being dispersed by the raindrops. You see, sometimes can be quite painful, especially when it hits our face, which is very sensitive. Okay, so that is how much the energy being dispersed into the soil surface. Okay, Okay, detachment, it adds to the sediment load. Once the soil particle is detached from its bond, so basically it's very loose and it can be transported easily. Okay, sediment load, what is sediment load? The rate of sediment that is transported downslope by the runoff. Okay, so what is load? Load is basically discharge whenever discharge which when the unit is meter cube per second and multiply with the concentration of sediment. Okay, so when we are talking about sediment load, basically water flowing with sediment inside it. Okay, so if there is no erosion, only water, but when we have erosion, there is a sediment inside being transported together with the water, so we have sediment load. Okay, so the unit of the discharge or the Q is meter cube per second, and concentration of the sediment is milligram per liter. So when we divide that, cancel out, Q meter cube and liter is the same unit. 1000 liter is equivalent to 1 meter cube. So now the unit become milligram per second. Okay, next. Okay, so this is the graphic description of process of detachment. Okay, so the detachment is basically the loosening of the soil particle, and then the surface runoff transport it becomes sediment load. Okay, next slide. What is sedimentation? So that when we have this erosion, then we have sedimentation, because this erosion happens with this eroded material, soil being eroded, and then it being transported downstream. Okay, and whenever it settles down, that is what we call aggradation. Aggradation of sediment is what it means is that it increase the amount of sediment at that place. Okay, due to siltation or sedimentation. When does it happen? Sedimentation. It happens when the transport capacity of the flow or the velocity of the flow becoming less, when and the transport, because sediment also has its density. When the density or the settling velocity is higher than the transport capacity, then the sediment will be deposited at that area. So where will be basically this sediment be deposited? Is normally deposited when the velocity of the flow become very much less. For example, like near the check dam, some culvert, in front of culvert, sediment basin, and so on. Okay. Okay, basically it's the build-up or gradation of sediment and land surface or the bed of a watercourse. Okay, next slide. Okay, basically deposition, when they deposit the sum of the material, so it reduce the sediment load. Okay, for example, like whenever the material is eroded and transported, the material is not uniform. Some of these materials or the soil are quite dense. Okay, for example, like sand. Sand is denser than silt or clay. Okay, so whenever the velocity reduce a little bit, so this heavy material will be deposited the earliest. Okay, and then the lighter material will be deposited later when it comes to sediment basin or check dam, and the very light material sometimes it will not be deposited, because the density of the material is less than the density of water. Okay, therefore it cannot be deposited unless it clump together. That's why in certain cases when we have this a lot of this clay material, so how can we deposit it when it is very light? So we add some chemical coagulant, so to allow to remove the some of this static charges, so that allow the clay material to clump together, become bigger, and then only become denser. Then only it can be deposited. Okay, So you have to add chemical like coagulant, polyacromate, and so on, so much to allow this material, clay material, to clump together and being deposited. Okay. So basically, deposition adds to the soil mass. Local deposition, surface roughness depression. Okay, so when we have on our surface, for example, like the surface runoff when it flows on the vegetative strip. Okay, when we have this grass and so on, the surface roughens. So that's why we have some deposition there. Okay, and okay, row middle where we have this is some of the material uh, we did in the in our construction site. Okay, remote deposition, concave slope, strips, terraces, and so on. Okay, next slide. Okay, this is some graphic description on the process of deposition. Sediment load, and then we have some sediment will be deposited earlier, especially the heavier materials. It can be easily deposited whenever the velocity changes slightly. So the denser material will be deposited earlier. Okay, next slide. Okay. Okay, what are the erosion potential? uh, what are the factors that influence erosion rate? Okay, one of the main factors in uh, erosion potential is soil erodibility. What does it mean by soil erodibility? So soil erodibility means that the tendency, how easy for soil particles to become detached by the action of the agent of erosion. Okay, so how easy of the soil to be eroded. Of course, different type of soil will have different erodibility factor. So which one is much more easier to be eroded? Sand or clay material? Okay, which one is easier to be eroded? Okay, the soil type of sand or soil type of clay? Okay, anyone?
Sand.
Salah, wrong. As you can
Clay.
see, as you can see, right below it, seal and very fine clay is the most erodible. Okay, so the finer the material, the easier that it can be eroded. Okay, so as you compare sand, which is much coarser compared to clay, which is very fine, so clay is a lot easier to be eroded as compared to sand. Okay, similarly, seal is somewhere in between sand and clay. Okay, next slide. And then another factor that can influence erosion rate or erosion potential is vegetative cover. What is this vegetative cover? Vegetative cover is a strip of grass or shrubs or bushes that we normally keep inside within our project area, especially near the boundary. Okay, so that this can protect erosion, soil from erosive forces, raindrops, such as grasses and bushes and shrubs and so on. Okay, so because bushes, shrubs, grasses, it can protect the soil from erosive forces. Okay, because when energy heat, the rainfall energy or the rain drop hits the grass or the bushes or shrubs, the grass and the bushes and shrubs can absorb the kinetic energy from the raindrops. So therefore, it will protect the soil. Okay. So with this, what we can suggest from this is that since we know the importance of this vegetative cover, so beforehand, before we start project, we have to plan. We have to divide the area, the development area, into a number of phases. Okay, because if we clear all the area within one shot, then we're going to expect a lot of erosion. But if we divide the development area into a number of phases, for example, like we want to develop phase 1 first, we leave the other phases with green area. Once this area has been cleared and they start construction, then only we move to phase 2. Okay, and then we move to phase 3. Okay, and phase 4. Okay, so if we do it in one shot, then we're going to face problems, especially Malaysia is a country where we have a lot of rainfall. So for example, like if we open up all the area and then you do construction within first phase, so what happens is that the other phases area will be exposed. Okay, therefore that will encourage erosion. Okay, okay. I was involved in this project where they do this project area without phases. What happened is that the other area is bare area, bare soil, so there's a lot of erosion. And once the DOE want to seal that area or issue stop work order, so they asked me to come up with some solution. So we proposed to do turfing at that time, and the cost of turfing for the area is very expensive. It comes to more than 2 million, close to 3 million just to turf the area because the area is very huge. Okay, but they don't agree. So what we did is that we take all this oil palm tree and we cover the soil surface with oil palm tree and therefore allow the grass to grow naturally. Okay, so that saved them a lot of money. Okay, next slide. As you can see here, so the picture shows this is the embankment. Embankment, especially when you have slope, okay, steep slope. So if we don't protect the slope, you can see that it can become eroded. Okay, the eroded slope as compared to the embankment that has grass covering the embankment. So therefore, there's no erosion within that area. But the area where there is no grass, you can see erosion process is taking over on the slope on the surface of the embankment. Okay, so this is not good. Okay, sometimes this can cause slope failure and so on. Okay, so that is why we need to protect this embankment. Okay, the sooner the better, because embankment is exposed to high erosion because the velocity of the surface runoff is very high. Okay, next slide. Another erosion potential is topography. Okay, what is topography? Basically, topography describes the elevation of the area. Okay, so the parameters of the topography that influence the rate of erosion is long slope. Okay, what is long slope? When you do cut, when you do fill, so sometimes the embankment is very high. So that is the long slope. Okay, so this long slope deliver more runoff and this deliver more erosion. Okay, so that is why to overcome this problem of long slope, what we normally do is that we do terracing. Okay, we have slope and then flat area and then slope again, flat area. So that is what we call terracing. Basically, terracing breaks the long slope and reduce the long slope to a acceptable length of the slope. Okay, and then we have steep slope, slope steepness. Okay, slope steepness basically depend on the slope 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 steepness is the slope angle lah. Okay, the steeper the slope, the higher the surface runoff velocity. Okay, so which one produces more erosion? Slope 1 to 1 or slope 1 to 2? Huh? Which one produces more erosion rate? Embankment of slope 1 to 1 or embankment of slope 1 to 2?
1 to 2.
Why? Huh? Basically because of
1 to 1.
one slope. 1 to 2 is milder slope, so less erosion. 1 to 1 is steeper slope compared to 1 to 2. Okay. Next slide, please. Okay, so these are some of the characteristics which can affect the erosion potential. Okay, one is vegetative cover or the cover of the surface, such as grass, bushes, shrubs, and so on. The other one is soil characteristic. Okay, whether the soil is sand, clay, or silt, loam, and so on. And the other parameter is the topography, slope length, and the slope steepness. Okay. Next slide. And the other parameter is which can influence the rate of erosion is the erosion potential. Okay. The erosion potential. Okay. Such as rainfall characteristic. What are the rainfall characteristic? The rainfall characteristic are the frequency of the rainfall, the intensity of the rainfall, and the duration of the rainfall. Okay. The frequency, what does it mean by frequency? What does it mean by frequency? Hello? What does it mean by rainfall frequency? Hello?
Number of rainfall happens in a period of time.
Yeah. How frequent is the rainfall? Okay. So in Malaysia, normally the rainfall is quite frequent during the monsoon season. Almost every day we can experience rainfall. Okay. So basically, which one will have higher erosion? Frequent rainfall or less frequent rainfall?
Frequent rainfall.
Yeah?
Frequent rainfall.
Yeah, frequent rainfall. The more frequent rainfall, the more erosion will happen. That's why in our country, in Malaysia, especially, we have to pay particular attention at the time when we do our land clearing. Okay, we try to avoid land clearing during the monsoon season because this is the time when we have plenty of rainfall. Okay, so this is part of non-structural management where we can avoid erosion by just planning properly during our construction. Okay, so we try to avoid during land clearing or earthwork during monsoon season or rainy season. Okay, that is frequency. Intensity, what does it mean? Intensity is the how intense is the rainfall, and the unit is millimeter per hour. Okay, which one produces higher erosion? 10 millimeter per hour rainfall or 50 millimeter per hour rainfall?
50.
Yeah.
50.
Yes, 50. The more intense rainfall, the more erosion. Okay. And then the other parameter is duration or the length of the rainfall. Okay. Sometimes the rainfall can be the length. I mean the duration of the rainfall can be 30 minutes. Sometimes 1 hour. Sometimes 3 hours. Sometimes 1 day. And during monsoon season in the East Coast, it can go up to 3 to 5 days without non-stop. Okay. So which one produces more more erosion? Shorter rainfall or longer rainfall?
Longer.
Yeah, longer rainfall. The longer the rainfall, the more erosion. Okay. Next slide. Okay. Now we're going to look at the types of erosion. Okay. There are many types of erosion type. Okay. One is interreal, ephemeral gully, permanent incised gully, stream channel, and so on. So we later on the slide will show you what are these types of erosion. Okay. Next slide. Okay. We have this definition for soil loss and sediment yield. Basically, soil loss is the erosion within the area, and then it's being transported. It's being transported. Some of it will be deposited along the way, but whatever reaches the point of interest, such as the river, that is what we call as sediment yield. Okay. Okay. So basically, the difference between soil loss and sediment yield is that soil loss is the eroded material that has been transported. Some of it will be deposited. So that is what we call as soil loss. But once it reaches the point of interest, we call it as sediment yield. Okay. Next slide. Okay, so this is similar, the definition for soil loss and sediment yield. Next slide. Again, this is for complex loop. Okay, next slide. Okay, these are the description of the various type of erosion. We have raindrop erosion or splash erosion. We have sheet erosion on the surface of the ground. And then we have reel and day and gully erosion. Okay. So basically reel is a smaller line and gully bigger eroded area. Okay. Next slide. Apa guna ni atas? Okay, so this is description, the differences between sheet, reel, and ephemeral gully erosion. Okay. The green color is basically sheet erosion because it covers the surface, the ground surface. Okay. We nak vacuum tak apa nak atas? Boleh. Okay, then when we have this thin black line, this is what we call as real erosion. When once over the time the thin black line become bigger, we call it gully erosion. Okay. Next slide. Maybe nak vacuum. Okay. The mechanics of erosion. The splash erosion. What happens during splash erosion is when the raindrop impact, okay, causes the soil particle to be dislodged, or it breaks the bonds between the soil particle, resulting in the dispersal and mobilization of the soil particle. Okay, that is splash erosion. Okay, next slide. Sheet flow erosion. It is a uniform removal of saturated soil. It's on the surface. Okay, uniform removal of saturated soil particle conveyed in the runoff water. Okay, that is what we mean by sheet flow erosion. Okay. Next slide. And then we have real erosion. So the difference between sheet erosion and real erosion is that real erosion is a long, narrow depression of soil incision. It's just a small cut on the surface of the ground. So this is what we call as real erosion, caused by increased topographic relief and higher runoff velocity. And usually, real erosion, the width of the what we can call it a smaller drain is less than 30 centimeter deep. Okay, or the depth of the drain is less than 30 centimeter depth of the drain. Okay, next slide. And then real erosion, normally over the time it becomes gully erosion. Okay, it becomes bigger. It is called gully erosion. Okay, when the incision channel that begin as real become bigger, wider, and deeper by the concentrated flow because of the surface runoff that flows within it. Then it cause eroded further. Then it becomes gully erosion. Okay, so when it becomes gully erosion, it becomes very highly effective as conveyors of sediments. Okay, next slide. Maximum erosion rate. When does it happen? Maximum erosion rate happen when the raindrop, splash, and sheet flow occur simultaneously. Okay, so it is raining and at the same time we have surface runoff. So this is when the erosion rate is at its maximum rate. Okay, next slide. Okay, the impact of storm events. Okay, during storm, the splash erosion happens when the raindrops impact, which produces the erosion producing power of the raindrops equal to the kinetic energy of the 30-minute intensity rainfall, maximum rainfall intensity. Okay, so basically we are looking at we assume that the erosion producing power of raindrops it comes from the kinetic energy multiplied with 30-minute intensity rainfall intensity. Okay, so what we will normally do is that we're going to get the rainfall data and we find the maximum 30 minutes rainfall intensity. Okay, which is the maximum rainfall intensity within the 30-minute storm. Okay. Sum of this in the area during an average year is equal to rainfall erosion index. And then we sum of this rainfall intensity in an area during an average year equal to rainfall erosion index. So rainfall erosion index is basically derived from the maximum rainfall intensity of 30 minutes within the area. Okay. So we have say that we have 20 years of data. So we find the highest for every year and then we average it out. Okay. Next slide. Okay. Why do we need to do all this soil loss estimation and so on? So basically, there's a need to uh, to to do some decision making process, because in the to give in to guide in making methodical decisions in soil conservation planning. So we need to do some soil conservation planning whenever we do development within a project area, so that we don't want all this material will be eroded and transported outside of the site. Okay. So that is why we need to estimate the erosion rate and then propose some mitigation to how to prevent it from happening or from leaving the to prevent erosion rate from happening and to prevent the erosion or the eroded material from leaving the project site. Okay. The equation enables the planner to predict the average rate of erosion for various combination of management techniques on a site. Okay. So the equation enables the planner, the person who plan to predict the average rate of erosion for various combinations of management techniques on a site. Okay. The soil loss equation estimation is a set of management of strategies for preventing of soil and eroded material from the earth's surface or becoming chemically altered by overuse, acidification, salinization, or other chemical soil contamination. Okay. So basically, this soil estimation is a set of management strategies. How do we plan? Okay, to prevent the soil being eroded from the earth's surface or becoming chemically altered by overuse. Okay, by acidification, salinization, and so on. Okay, next slide. Okay, application of soil loss in civil construction. In a civil construction project, soil loss estimate is used for the following activities. Okay, in the construction site, that's what you are going to do in this semester. You're going to plan the erosion control for a construction site. Okay, we will give you the construction site, and then you have to plan the erosion and also the sediment control. Assessment of the project potential erosion hazard associated with the given project. So you are going to assess the potential erosion hazard. Okay, if it happens so that your project area, the location of the project area is sited within a very sensitive area. What does it mean by sensitive area? It can mean that the project site, when it is exposed, it contains a lot of this clay material, easily eroded material, or the project site is located near water bodies, rivers, lakes, and so on. So we have to prevent this area from being contaminated. Okay, so that is why we need to do the potential erosion hazard. Whether the area is located within a very sensitive area or not. Okay. Identification of high-risk construction projects during the planning or design phase. Okay. So we identify the construction risk, like I said just now. during the planning, we have to identify whether there is very high risk or what. Okay. Assessment of the relative performance of alternative soil conservation practices. So based on this parameter, how sensitive is the area, so we have to propose some mitigation. Okay, and then we have to assess the performance of the mitigation facilities. For example, like we constructed a number of sediment basin. Okay, and then we have to assess how efficient is the sediment basin in filtering out sediment. Okay, sometime over the years, over the time, the performance is going from high to low. Why? Because there is lack of maintenance. Okay, for example, like the sediment basin, when it was first constructed, the efficiency is about 90%. But over the time, when the sediment basin is filled up with sediment, so it becomes less efficient. It reduced to 70%, 50%, and then it can go to less than 20%. Unless we do the maintenance. For example, like we have to remove the deposited material and bring back the storage volume. Okay. So the assessment of the performance is very important. Okay. So because if not, the efficiency will be less and less, and therefore more material will be transported outside of the construction site. This is what we don't want. We want it all to be trapped within the project site. Okay, so that is why we need to assess the performance, the relative performance of the soil conservation practices. Okay, next slide. What is soil loss? Soil loss is the amount of eroded soil that is delivered to a point in the watershed that is remote from the origin of the detached soil particle. So soil loss is the amount of eroded material, whether it's silt, clay, the eroded material is being transported to the point of interest. Okay, for example, like in rivers, water bodies, and so on. Okay, next slide. In watershed, soil loss includes the erosion from slope, embankment, slope, channels, mesh weighting, minus the sediment that is deposited after it is eroded before it reaches the point of interest. Okay, because some of the sediment load will be deposited along the way. So basically, soil loss is the amount of eroded soil minus the deposited material. Okay. Next slide. Okay, soil physical properties. Okay, so as we have earlier described, the different type of soil which has different type of correct soil erodibility factors. So we have various type of soil. We have varicose sand, where the diameter is 1 to 2 millimeter, and to the fine material like clay, where the diameter is less than 0.002 micron millimeter, or 2 micron, 0.2 micron. Okay, these are the various sizes of the soil. Okay, we have coarse sand, medium sand, fine sand, and so on. Okay, next slide. Okay, to describe the various type of soil diameters, or the soil particle diameters, you can see that the bigger size is fine sand, and the smaller size is clay, which is very small as compared to sand, fine sand. Okay, this is to fine sand, not coarse sand. Okay, the relative sizes of the soil properties. Okay, next slide. Okay, so the soil texture, because Normally the soil type is not homogeneous. Very rare we can find homogeneous soil where the soil type is only clay, only sand. So normally it's mixed. Okay, so the soil texture is based on the percentages of the soil types. How many percent clay, how many percent sand, how many percent silt, and then based on that we can categorize, divided the soil based on the texture. Either it's clay, whether it is sandy loam, clay loam, silt loam, and so on. Okay, so we use the soil texture taxonomy to identify the soil texture of that area. Okay, next slide. Okay, the prediction of the equation. Okay, universal soil law equation. So how can we estimate the erosion rate? So normally we estimate the erosion rate using this equation. Okay, so basically in this class we are going to use the revised UCLE and the modified USLE to estimate the soil loss and the sediment yield. Okay, next slide. Universal soil loss equation, USLE. Okay, next slide. So what does USLE do? USLE computes average annual soil loss. Basically, we use USLE to estimate the average annual soil loss caused by sheet and rill erosion, due to sheet and rill erosion. Okay, it applies to overland flow on slope, compute sediment yield from slope, computes deposition on slope, and also compute soil particles. Okay, next slide. Why do we use USLE? USLE is a tool for conservation, soil conservation planning. Okay, we have to conserve the soil because this soil contains nutrients where the plant needs to grow and so on. If we allow the topsoil to be eroded, then the soil become less fertile. Okay. Okay, USLE is a tool for conservation planning to assess the BMP effectiveness. Okay, whether our proposed mitigation is effective or not. So we can use UCLE to assess the performance goals. So what are our performance goals in maintenance, soil conservation? Okay, so using USLE, we can assess the performance goals. Okay, and then achieve sustainable use of soil resource. Okay, prevent excessive sedimentation. Okay, prevent degradation of water quality and so on. Okay, but not for water quality enforcement. Okay, next slide. What kind of land do you use to estimate soil loss? Cropland, agricultural land, construction site, disturbed forest land when we have logging. Okay, rangeland, surface mining, reclaimed land, landfill, and so on. So these are the places where we can expect erosion happening within that area. So therefore, we can use the equation to estimate erosion from this area. Okay, next slide. Why is USLE widely used? Basically, it's being used all over the world. Why? Because it is very easy to understand, very easy to use, and it requires minimum resources. Okay, we don't need a lot of data. Okay, input values readily available. Okay, independent of land use. Okay, depends on varies with different type of land use, and it's been used for almost over more than 50 years already. It's been used. Okay, in many countries throughout the world. Okay, next slide. So basically the erosion rate, we call it, the symbol is A, or annual soil loss rate. A is equal to R is the rainfall erosivity, C is the crop management factor, K is the soil erodibility, topography is length, slope and slope thickness, slope length and slope thickness, erosion control parameters, and so on. So basically, A equal to, next slide please, R multiply with K, multiply with KLS, multiply with C, multiply with P. So there, from there we can get the average annual soil erosion rate, or the unit is ton per hectare per year. Okay, so that is A, average annual soil loss, soil erosion loss. And the unit is ton per hectare per year. What is R? R is the rainfall erosivity factor, which depends on the, how do we derive R? It based on the rainfall erosion index, based on the intensity, 30 minutes intensity rainfall. Okay, that is R. Is rainfall erosivity factor. K is soil erodibility factor, which depends on the easiness of the soil to be dislodged or being eroded. And the unit is ton per hectare per hour divided by per hectare per million joule millimeter. Okay, that is soil erodibility. And then you have this L, which is which is the slope length factor, and the S is the slope thickness factor, and you combine it become LS factor. And then you have cover management factor, and P is the conservation practice factor. So you multiply all that, you get the average annual erosion rate. Okay, which is the unit is ton per hectare per year. Okay, next slide. Next slide. Okay, so this is how we derive the rainfall erosivity factor. Okay, the rainfall erosivity index R is calculated from equation as shown below. R equal to 1 over n summation of energy, kinetic energy, total storm kinetic energy multiply with the intensity of 30 minutes. Okay, the total storm kinetic energy for each storm, E is obtained by summation of the product of unit kinetic energy and the respective rainfall volume of all the increments in a rainfall event. Okay, so that is how we get the energy E. E equal to summation of E small e multiply with F, or the rainfall energy, unit kinetic energy, and the respective rainfall volume of all the increments. Okay, K is the number of storm intervals, R is equal to index of storm intervals, E is equal to unit kinetic energy for the ice interval, V is the rainfall depth for interval. Okay, so that is how we determine the R, okay, or the rainfall erosivity factor. Okay, next slide. This is how we derive the rainfall erosivity factor based on the storm data collection. Okay, we take the storm data based on 10-minute rainfall interval. Okay, and then we do the clearing, data clearing and separation, and then we accumulate 1 day EI 30. Okay, and then we accumulate the monthly EI 30, And then we come up with the annual rainfall activity. Okay. Based on that, we average it yearly to get the R factor. And that is what we call as the soil erodibility factor. Okay. Okay. Next slide. Okay, rainfall erosivity factor is, and then we come up with this map. We call it the map of rainfall erosivity. The ISO eroded map for R factor are generated using GIS. So we have many rainfall stations. For every station, we have the R. Okay, so kita guna GIS. We use GIS to generate the map for what we call as rainfall ISO erosion map. Okay, the method used for this interpolation is kriging. Kriging method. Kriging is based on statistical method with that include auto correlation. Okay, that is just statistic in relationship on the measured points. Okay, next slide. Okay, this is basically the concept of geostatistical kriging method. Based on this, when we do the interpolation for various rainfall stations, we come up with this ISO erosion map. Next. So this is what we call as the ISO erosion map or the R factor. So for every state, there is the map. So what, as a user or planner or engineer, so we just use this map to provide us the ISO erosion value R. Okay, so we just look at where our project location site, and then we look at the color, and then the color for every different color, it has different value of R. Okay, next slide. So these are for various states, and one on the right hand corner is for the state of Johor. Okay, so for Johor, the range is between 11 to 16,000. The R value is 11,000 to 16,000 million joule, blah 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 blah. Okay, next slide. And this is for Terengganu and other states lah, Pahang and so on. Okay, so they have already come out with this map. So as a user, we can just use this map to identify our right R values for our site. Okay, next slide. And so on. Okay, and the other parameter is the soil erodibility factor, or K. K value. What is the K value? The K value is basically how easy the soil can be eroded. Okay, how can we determine this factor? We can determine this factor by using nomograph or by using the equation. Okay, as the equation is 100K is equal to 1.0 m power 1.14 and so on. Okay, what is M? M is the soil characteristic or the soil texture. How many percent silt? How many percent very fine sand? And multiply 100% clay. Okay. And A is the variable A is the percent of organic matter within the soil content. Okay. B is the soil structure code and C is the permeability class. So all these factors can be obtained by taking soil sample at site. We take the soil sample aside, bring it to the lab and do sieve analysis. And from there, we can determine our soil factor, soil erodible factor. Basically, we will do at different depth, less than 1 meter and 1.5 meter, and then we average it out. Because some of this area, when we do some area cut, we can cut up to 1.5 meter. So the exposed soil is 1.5 meter deep. Okay. So that is why we need to do various depth and then we find the average value. And then we normally do not only for 1 point, based on the borehole, we can get about a few points and then we average it out. Okay, next slide. Next slide, please. Okay, the soil erodibility factor is the rate of soil loss per unit of rainfall erosivity vector or EI30 for a specific site. It is measured. It can also use measured using a plot. Normally the plot is about 22.1 meter length of uniform 9% slope consistently in clean till fallow. Okay, so this is another way of how we determine the K value. Okay, the soil erodibility are affected physically features of the soil, topography features, and so on. Okay, next slide. Okay, soil erodibility can define the resistance of the soil to both detachment and transport. It is important index to measure soil susceptibility to water erosion. So it's important to determine this K because this soil K basically is the resistivity of to erosion and so on. Represent the soil erodibility factor K represent the effect of soil properties and soil profile characteristics such as soil texture, aggregate stability, shear strength, infiltration capacity, organic and chemical content on soil loss. Okay, next slide. Okay, so when we're talking about soil layer, determination of soil properties, we have different layer. So soil layer A, or normally we call it as horizon A, is the surface soil. So between the depth is between 0 to 0.5, and soil layer B is the subsoil, 0.5 to 1, and soil layer C is between 1 to 1.5 meter. Okay. Okay, next slide. Okay, the M value, determination of M value, which represent for very fine sand and clay content. And this equation can be obtained from particle size distribution. When we do the sieve analysis, we'll get the particle size distribution of the soil from test of wet or dry sieve analysis. Okay, so I think we stop until here because it's already 4 o'clock. So we'll continue in the next meeting. Okay, so you will have briefing from other lecturers, and then after that we'll meet again. So you can read this material, and then if you have any questions, you can also ask. Okay, WhatsApp me or you can always ask. Is there any question? Huh? Any question?
No, doctor.
No.
Okay, if there's no question, then okay, go ahead and study the slide, and then we'll meet again sometime later on. Okay. Okay. Bye.
Okay, thank you, doctor.
Thank you, doctor.
Welcome.
Thank you, doctor.
Bye.